streams going on here. And I've never presented in the round before, so this should be fun. So, yeah, I'm Dr. Drew Butner. I'm in the chemistry department. And my sort of backwards stumbled into analysis of food, but I do a whole bunch of other things. But we're going to focus today on the analysis we've done of beer and of kombucha. But you'll see reference to some other things. And as Dr. Wakefield says about begging for money, the first thing I have to do is thank the people who gave me said money, right? So this work is, I'm presenting it, so I get to take all the glory. But it's really, most of this work was done by the list of students you see here over the last 2 years. So some of it work's a little bit older, but the lion's share of it's been done by these undergraduate students over the last 2 years. And you can see it's a fairly large number. I think 5 or 6 of them are either have graduated or are about to graduate. So we have a large group. And it's split over the kombucha, the beer, and also honey. I don't think I have time to talk about honey today, but we might. So depends on how fast I talk. So that's a small section of them there. This work is funded in part by the SC Emory, which is who you have to sign in for. They've helped with some of this, but also the Analytical Society of Pittsburgh and their conference has a small undergraduate research grant that I received to help support some of this work. And then Coastal gives me some more work, so I find pennies and we put them into beer. So the areas that we're going to talk about, and this is sort of the broad areas that I am sort of interested in studying, broadly fits into 2 categories. This idea of we're developing or doing some sort of quantification methods for what are really complex samples, right? And we're looking at both macro compounds, large amounts of things, but also some of the minor components as well. And that's broken down into analysis of these gluten-free beverages. That's my code word for beer. Kombucha, and then honey. And then in the past, and previously, and if somebody speaks loud, I may do it again. We've done some hydrogen peroxide in environmental samples and biological samples. We've used hydrogen peroxide as an electrode sensor material for things in environmental sampling and biological. But then I'm also interested in some pedagogical work that I teach. Right? So we talk about alternative assessments that we have, and then student motivation of learning. So of all these things, we're going to focus on these first 2, the analysis of gluten-free beverages and kombucha, because it tells a nice story. Apparently that did nothing. All right, so I say gluten-free beverages because it's a nice way to say beer, right? And there's sort of a gray area whether what we do is actually beer or not because of the shortcuts we take. But we're interested in gluten-free beer for a variety of reasons. It started out because I was collaborating with somebody who was doing some bioinformatics on celiac disease. For those of you who don't know, celiac disease is the largest sort of gluten-intolerant disease in the world. About 1 in 133 European descendants have celiac disease. And that number seems to be growing because every time I ask, does anybody here have celiac disease? So you now all know somebody who has celiac disease, right? And because of this increased awareness of celiac disease and also sort of the popularization that gluten is bad, I'm not going to have that discussion, but we've seen a preponderance of these gluten-free materials come onto the market. And that includes in commercial brewing. I just this week saw an advertisement for a head brewer for a brewery in Oklahoma that was starting to focus on gluten-free beers. Right? So when we talk about gluten-free beers commercially, they usually have been made predominantly from sorghum under the large-scale market. But in the craft brewing industry, the smaller brewers, they have a lot more freedom and flexibility to play, so they will make stuff with sorghum, but also millet, buckwheat, rice, quinoa. I've seen beers made with lentils, sweet potatoes, a variety of things, as long as it gives us fermentable sugars and doesn't contain gluten. Right? So if you don't, we'll come back here in a minute. Right? And it's not uncommon, like different cultures have been brewing these beers or these fermented beverages with whatever grains were available, products that were available, right? And including some of these. So if we look at sorghum, I'm not going to try to pronounce that word. It's a South African traditional beer. It's openly fermented from sorghum, right? I hear it has a very unique flavor. I've never tried it. Has anybody tried that? Okay. If we look at millet, which is sort of, we have Bantu beer, which is throughout Africa as well, and is also supposed to have a fairly unique and strong flavor. People really enjoy that one. And then we have this Raski, which is Nepalese, which is their distilled, the thing that they ferment before they do the distillation for the distillation liquors, right? So we've been using these materials to produce fermented beverages for millennia, right? We are just now in the U.S. discovering them, if we can say that on this close to Columbus Day, right? These beverages, right? And what we're interested in is if we look at where our flavor comes from in beer, right? So for those of you who don't know how to make beer, beer is actually fairly simple. You take some sort of a grain and you allow it to start to germinate, and that's going to allow the seed to actually start that process of converting that stored starch into simple sugars, right? We allow it to germinate a little bit with in the presence of water and a little bit of heat, right? Until we sort of get it to germinate, and then we sort of kill it. And that killing process, we also can add additional heat, right? That sort of stops that conversion. Also, depending on how hard and how long we heat it, it's going to give us some additional color, right? And that product is referred to as malt, right? So one of the sources of flavor in these beverages is going to come from the source material or this malt in beer, right? And it has those, those organic. This is my slide for the organic chemists in the room, right? Organic molecules. We also then take that malt and we introduce it into more water that's hot and allow the enzymes that are present in those grains to reactivate and complete some of more conversion of those starch molecules into sugars, which are then extracted into this solution, this warm water solution, right? We drain that off of the grain, and that is called wort. And then we heat it up to sort of do a variety of things. It goes into a boiling process, one to help precipitate some proteins, help filter out some of the solid material that's left over. We also kill the enzymes and any other bacteria that or microbiology that's there so that we can introduce whatever we want to it. Right? At that point, or somewhere in there, we have this very sweet, sugar-laden material, right, which has other things in it, but predominantly it's very sweet. So to counteract that sweetness and also to add some additional flavors and help preserve the beverage long term, we add hops, right? So you can see the hops aromas there, right? And that's going to do two things depending on where we add the hops to the beer. If we add it early, it's going to primarily add acidity and counterbalance some of that sweetness. If we add it late, it's going to primarily form the aromas that you all associate with beer. Right? Those are all coming from the hops. And then finally, we cool that down and we introduce our thing that was going to do the fermentation, this yeast. And the type of yeast that we use has some role in determining our aromas and our flavors at the end. So we have these sort of three key ingredients to determine flavor in beer. But there you'll see there some sort of source material, some sort of microbiology, and as well as some sort of additional flavor additive. That's true in beer, and we'll see it's also true in kombucha. Right? So for our work, because we want to sort of specialize in what's coming out of the grain, right, we don't hop any of our beers just to reduce the total number of compounds present. And we'll add a specific yeast strain. We have a standard one. It's an American ale. It's called USO5 that we typically use, but we've also used some other ones. So what we're trying to do is distinguish what chemicals are coming out of this grain and how those chemicals differ either in actual identity or composition for these gluten-free grains versus traditional barley-based beers. Right? So the project objectives in a whole, if we can summarize the last 10 years of my life into 4 bullet points, right, is to characterize beer brewed with these gluten-free grains. Primarily, we're going to focus today on sorghum and millet. We have done some work on buckwheat. We've done an introductory work on quinoa, using common measures of fermentation, right? pH, total phenols, titratable acidity, something called FAN, free amino nitrogen, and sort of characterize it. Are we still producing good beers? Is essentially what we're doing, and how did those beers compare to the barley ones? Right? And then we're going to do some indication of how in those bulk schemes they differ between these gluten-free grains and barley. But we're also going to do what's referred to as a non-targeted analysis of the volatile and semi-volatile compounds using headspace GCMS. Right? Which is a very fancy term. We're just going to throw stuff in the GC and see what happens. Right? We're not looking for anything in particular, which is why it's called non-targeted. We don't know what those compounds are, except for they get into the gas phase. They're volatile or semi-volatile. Right? And we're not looking at anything in the liquid fraction right now. And then once we sort of have an understanding of how those grains differ, we're going to investigate the impact of yeast. And we've done this for sorghum, and you'll see that today. We will probably do it for millet in the future, but we aren't there yet. And then buckwheat further on, that's because I have to get more. And then finally, I had the opportunity to take a sabbatical or a scholarly reassignment. That's the correct term, right? I was out of the classroom last spring where I had the opportunity to partner with a local brewery. We brewed a series of gluten-free beers, all of which individually were unique. And we were able to get some customer feedback both on the individual grain beers, but also in a finished product. So we've done some of that. You'll see a little bit of that today for the millet-based beer. Okay. So let's talk about the brewing in coastal. So, so this is my fancy brew system. It doesn't look that nice. It's currently stuck in a hood. It's a 3-pot system, and for the first work we had for sorghum, we were taking a shortcut using what's called malt extract. So somebody else did the steeping of the grain, took out all of those simple sugars, and then condensed it, concentrated it so it became like a syrup, and that's what we used, right? So we used either that sorghum syrup or this amber, which is a barley-based syrup. And at first, the first runs that we did some like 60 different unique brews with this US-05, an American ale. And then we came back and we looked at impact of yeast using these 4 additional yeast, a different strain of American ale, a British ale, an American wheat, and Belgian Abbey. So it's all top fermenting yeasts to sort of understand how the impact of this yeast culture is what we're going to see. And we brewed for fermented for 14 days, and we took time points before we started fermentation, after 3 days, after 7 days, and after 14 days. We have a little bit of data at 10, but those were the ones we took. Right? And we chose those days because we wanted a baseline, which is coming straight out of the grain or the beer. After 3 days, much of the initial fermentation has happened. Right? Most of the sugar has been consumed. We've created all these compounds. 7 days, that's almost completely finished, and we're starting to add some complexity with some additional reactions. And then 14 days, fermentation actually has stopped. A lot of the flavor would be sort of matured at that point. And that's a pretty common time frame for these beers. We're going to focus on now just the volatile, semi-volatile space using this GCMS. So either side we have our GCMS system using something called headspace SP or SPME. Right? So you can see in the left side of the slide, we have a fiber that's inside of a needle. Right? So we can expose that fiber to the headspace, the gas above our solution, our beer. Compounds will preferentially stick to that fiber over time. We can then take that fiber, put it back in the needle, transfer it into our GCMS, heat the crap out of it. Those compounds will come back off. We were then able to separate those compounds from each other, and using mass spectrometry, we're able to give a rough estimate of what idea, I guess would be a better term, of what compounds are present. Those are the conditions. If you're an analytical chemist, those are important. If you're not, don't worry about that. Right? So what we can see just initially, just looking at the results of these chromatograms, what comes out of the GCMS. The top one is barley, the bottom one is sorghum. Over those, I think this has an additional 10-day time point. What you can see, two things that I want to point out with this graph. One, regardless of whether we have barley or sorghum, as fermentation occurs, the concentrations of things are changing. We can see that by sort of looking at that middle peak. You see where it's the 1,2,3 trimethylbenzene. The peak right next to that, as you go up, you can see the color changes because the concentration, the relative amount, is changing with time. Right? 2-heptanol is actually our standard. Why we add that to make so we can estimate concentrations of other things. It's not changing, which is on the bottom scale. But also, if we look just holistically at barley versus sorghum, right, those two pictures look different. Right? Maybe not greatly different. I mean, if you're not used to staring at GCs or mass chromatography, like they just look like a bunch of squiggly lines. Right? But if you look, the top one's more squiggly than the bottom, right? Which means that there's probably a different composition up there. And it's again, if you look around that 1,2,3 trimethylbenzene point, right, that's at about 15 minutes, right? If we come down to the other one at 15 minutes, that peak isn't there, right? So there is differences there. So that's one thing we want to see, and that those things change with time. Right? So like I said, we ended up doing 52 unique fermentations of sorghum and barley at the same time using USO5. Right? When we did that, we were able to find that 152 compounds showed a significant difference in concentration through fermentation. So either they changed, they increased significantly, or they decreased significantly. Right? Of those, 42 compounds were shown to be highly statistically different. Right? 18 of them were present in barley samples, 18 in the sorghum. The one interesting thing we found is that if we compare the two, we only found 9 compounds that were unique to either sorghum or barley. The vast majority of those compounds were found in both. Right? And when we look at that, we found about 40 compounds that were present in both, but the concentration, relative approximate concentration, was different in either barley or sorghum, right? So which again, in retrospect, makes sense. They're still grains, right? And a large portion of this is coming from some of it is coming from the yeast, right? We have the same yeast, which means metabolomically they're following similar pathways. So we should get similar things, right? It was sort of surprising to me and not as super exciting, right? Didn't think that hard because I wanted like a magic bullet. Like if we just take and add this one compound, we can make my sorghum beer taste like Miller Lite. We can't. It's not that easy. We can make Miller Lite out of sorghum if you want such a thing, but it's not that easy. Of these 40 compounds, we found 17 that were highly significantly different between barley and sorghum. And then we took that 17 and we took a subset of those. This is a list of 14. Right? I don't know why I went from 17 to 14. 17 probably doesn't fit as well on the slide. Right? But we took from this list, we took these compounds, and they were fairly easy to get. They didn't smell horrible. Right? So we decided to actually do a specific quantification on these, and we wanted to look at the impact of the yeast on these specific compounds, which we'll come to yet. But just to give you a sense, these are those compounds. We have the library identification, which is what the GCMS is calling them, sort of follows the IUPAC naming in chemistry. We also have the common name, which is common to the flavor chemists. It may not originate, like I don't know if Wakefield recognizes those common names. So like I talked about like 1-butanol or 3-methyl 1-butanol, right? And somebody was like, what is that? And they're like, oh, isoamyl? Oh, that's good. So that varies, right? But these are sort of the common things that we look. Some of those are nice flavors, right? Like banana. We might like banana in our beer. We probably don't want fat, though, right? So some of these are positive attributes and some of them are negative. And ideally, we want to accentuate the positive and sort of minimize the negative, right? Unless you like fatty beers, I don't know. But what we did then was we looked at these compounds, added those additional yeast strains, redid a bunch of fermentations to sort of see how that affected. And the easiest way to show it quickly is we have these pie charts. Right? The pies represent the total of all of those compounds after this 14-day fermentations. And what we can see is what you would expect is that they look different. Right? We get a different set of the yeast does have an impact on fermentation products, as we would expect, and those results are different. What we didn't find, which is again what I was sort of hoping for, is that I could throw like an American wheat yeast into a beer and get a composition that resembled an American ale with barley. Right? It's not that simple. Again, if it was, somebody else would have figured it out by now. But that's what we were hoping for, right? But this means that there are these significant differences, and yeast plays a role. Which, again, if you've done a lot of brewing, it makes sense. The way we capture flavors is by varying grain material and yeast, right? Along with water chemistry. So we're still in the process of sort of understanding how this works. The other thing that we noticed is, that's just a repeat of that. That there is an impact by yeast strain, but overall, the sorghum concentrations were lower than that of the barley. And I think I have a couple reasons for that, right? Sorghum, we don't get as much sugar out of. It's harder to extract. The yeast isn't sort of used to it, right? There's a variety of reasons for that. It just doesn't work as well. There may be, because I'm not very nice to yeast, I just took that distilled water and that malt and stuck it together, and not really caring what it did to yeast. There may be more viable, like there may be more nutrients coming out of the barley for the yeast than the sorghum. Right? The yeast just may be happier in the barley conditions because that's what they're bred to live in than in the sorghum. So there could be some reasons for that, but overall we saw that they were lower. Right? That makes sense. Any questions before that? Okay. So if we look at what we did at Tidal Creek, we brewed with sorghum, we brewed with millet, and we brewed a composite that had buckwheat and sweet potato in it individually. And then we did some tests on those, and then we mixed all three of those together, and they sold that because that tasted okay. But what we're going to talk about today, because it sort of fits the narrative, is we're going to talk about what we did with millet. So this was our first sort of brew of millet, and this is the conditions. Again, if you're into brewing, you see we did add some additional yeast nutrients in here and some additional enzymes to help our conversion of those sugars that's present in barley at a higher amount than in this sorghum. So we gave it a little bit of extra help. And what we can see is that we did three different, so that was what we did at Tidal Creek, that was what we were doing here, Coastal. We did three different brews, so if you look at the brew / number, the first number is the brewing schedule, so we ran three different brews, 1, 2, 3. And we monitored at day 0, which is what the 100 means, at day 7, which is what the 07, and then day 14. Right? And you can see for all of these, as we would expect, as we go through fermentations, the pH drops, and we see an increase in total acidity. As these yeast are doing their things, they produce, one of their byproducts is these organic acids along with other acids. Right? So we get a decrease in pH and a relative increase in total acidity. Right? If we look at the total phenols, which is sort of a mixture of those sort of biologically important compounds, we see that they are fairly high at the beginning, but they all decrease as the yeast sort of eats the things that are available. As you might expect, they're just eating stuff, so those go down. We did the same thing, and we don't have as much statistical significance on it. We just picked some of the ones that I saw were different. And you can see that we do get changes with fermentation, and these values, and I'm not going to show you the comparison, are different than what we saw in either barley or sorghum. Right? So we were doing these 4 different analyses, and we get, again, this is preliminary data. We haven't chanced the gut. All right. Now we go to Tidal Creek. Right? This is a little bit more involved because he's an actual brewer and not just a chemist playing in brewing. Right? So there's a lot more added here to make it an acceptable and profitable brew. Right? It was a bigger brew. We also added more enzyme. We also added a whole bunch of compounds to make the environment happy. So you'll see all of that affects water chemistry. Right? All of those things in the bottom left there are added to either balance pH or improve flavor. Because we know, and this will come up later, we have time, that the presence of these compounds has an impact on the perceived flavor of these fermented beverages. Right? And then we added hops. We added just a very basic acidic hops at the very beginning of the brewing, and then a flavor or a floral hop at the end. It was called whirlpool, right? It was when you stop boiling, you sort of spin it in a whirlpool. It helps all that stuff collect in the middle so you don't pump it out. Right? And if you're into fermentations, I'm assuming you guys have seen these before, fermentation profiles. Right? So we can see if we follow pH or specific gravity amount of sugar, we see that, again, in the first 2 days, both of those decrease. Right? The fermentation is happening. And we can see that it sort of levels off, which means fermentation is done. It happened really fast because this was a really weak beer, right? And you can see, again, I took a sample from what we had before we boiled it, from after we boiled it, and then after that finished beer at 14 days. So you can see the pH didn't really change through the boiling, but it did decrease after finish. But not as much as some other things, right? That's going to be a function of the fact that it turned out to be fairly weak. I think our alcohol percentage on this was like 4.5, so not great. But what it did allow us to do is actually try some. So I took random people who just happened to be at Tidal Creek and willing to try beer, and had them try it, and sort of ask them the question, do you like it? How would you rate the aromatic? How does it smell? How does it taste? How does it feel in the mouth? Does it linger? Do you get sort of the malty flavor? So do you get the grain material? Is it bitter? Right? And you can see there was a 5-point scale for each one of those. And you can see that most people didn't like it. To be honest with you, it wasn't good. I don't recommend you just take straight millet and try to brew it. You won't be happy. It tasted weird, but that's okay. We have other arsenals, right? But we also asked them an open-ended question like, what does this remind you of? What's the characteristic flavor? And we got this sort of weird cloud, which you can't see because it's yellow, unless you're on this side. You clearly can see it on this side, but not on that side. But it was flat. It was light. We had some thing. My favorite of all of these was the descriptor of garbage juice, right? Which I think is a little bit like mean, but that's what they felt. I think it was actually one of the people who brewed, is a brewer that put that on there, which I kind of sort of took offense to, but that's okay. Right? But some other people liked it, right? Beer is a very common thing, right? Everybody has their own unique flavor, and you don't not like beer. You just haven't figured out the beer you do like. There's a variety of different things. But I guarantee you're not going to have more than one glass of this. But we did see we were able to successfully do it. We did have pour extraction. We have since repeated it here at Coastal using a couple of different things to help, right? We did increase the mass temperature. We were sort of brewing it very similar to what you would brew with barley. Come to find out the gelatinization temperature of these grains is higher, so we actually have to heat it up higher. which means we had to add some thermally stable enzymes to get that extraction to improve. I think we've done that. We did it this summer. I just haven't had a chance to go through and compile the data for you all yet. And it was okay, right? Some people were maybe being nicer than they should have been. They thought it was okay. Some people thought it was just weak. Didn't really taste like much. Some people thought it was unpleasant. But we did have a chance to blend it with, so we took the sorghum-based beer, this millet beer, and a sweet potato buckwheat beer, mixed all three of those together, and they did sell that, and it didn't last very long. So it was okay. Like that was actually pretty good. I still have like 6 cans of it in my house if anybody wants one. It may not be as good now, but it was okay then. So we were able to, we can produce, and as you can see, commercial breweries do it. You can produce good beers with these, but they are different. One thing you have to be aware of, again, you can't go in expecting to get something like, you're not going to get Coors Light out of any of these. Right? You'll get a good beer, it just may not be what you're sort of used to. Okay. Questions about that? So from our experience in brewing beer, we just sort of through a variety of different options. My collaborator was writing and asked me to help write a review article about kombucha. One of the local kombucha producers asked me to do some investigations of kombucha. So we decided to start studying kombucha. Right? So we're going to now switch gears about kombucha, which is also a fermented beverage. Right? But it is significantly different than beer. That's for somebody else to say. What kombucha differs from beer is in the way it's fermented. So beer, we use a single strain of yeast, right, under anaerobic conditions. So we cut it off from the atmosphere. Kombucha uses what's referred to as a SCOBY, or symbiotic culture of bacteria and yeast. Right? So we take yeast and bacteria, and not even a single strain. We take a variety of them, right, and add this to the kombucha, and it's responsible for fermenting. And it also occurs aerobically, so we don't seal it off from the atmosphere. And the telltale sign of this fermentation is this pellicle, right, which is the biomass that sort of is left behind, and it looks like that, right? It feels like it looks, if you wanted to know. It's very dense. It's kind of gooey. It's not very appetizing, but it does what it needs to do. Right? So it's this characteristic of kombucha fermentation. Right? So for the study we did here, we said that when we did the beer, we added all of those different, like the gypsum and the sodium chloride, because it impacted the final flavor. Right? We know that very well in wine and beer, the impact that those ionic compounds have in both fermentation, but also final product. Right? So if we look at beer, for example, if you have a Pilsner, everybody familiar with the term Pilsner? Okay. It's called a Pilsner because it was first brewed in Pilsen, Czech Republic, and they have a very distinct water chemistry that allows it to be that smooth, sort of muted flavor. It's not overly harsh because of the amount of sulfate in it. So we know that really well with beer, but we haven't really studied it. We haven't, hypotheses that we have the same thing happen in kombucha, but it's not been studied. So our goal was to study the impact of water chemistry on these kombuchas, and we're looking at kombucha products, not necessarily the fermentation. So we were going to look at things that we looked at was ethanol. We want to make sure that it was not producing that much alcohol, because then you can't sell it. Right? But we're also going to verify that it conformed with standards in terms of total acidity, antioxidant, total phenols, caffeine, and a variety of other things. So what we did is we brewed different kombuchas using a single black tea type, and I guess we'll talk about the conditions. And we added either distilled water or specific concentrations of these ions, right? And we did 5 different ions at 3 different levels. We did a low level, a mid level, and a high level. Those levels span the concentration of these ions we would expect to find in a municipal water source. Right? So if we look across all of these, that's what we did. Right? And then we went back and we brewed some with the combination of all of those, a very low level total ions, mid level, and a high level. The ions that we looked at were calcium, magnesium, chloride, sulfate, and bicarbonate. Sort of those things that you would be able to see when you read a municipal water report. All of those are fairly commonly reported, and we know have an impact on chemistry. Put all these stuff on the slides, and I just talk about it. No. So what we did is we made the sweetest tea I've ever seen. Right? In a liter of water with the appropriate amount of ions, we put 8 grams of tea and then added 100 grams of cane sugar to it, right? Which is a boatload of sugar, literally a wayboat load full of sugar. It's really sweet. And I have some reasons for that. One, I didn't want sugar to be a limiting factor, right? I wanted all of our microbiome to be happy, right? So we're going to overfeed them. We chose raw cane sugar because it was cheap. Let's be honest, that was one reason. But also, it has a variety of sugar content. So if there's an impact on sugar type, I wanted to make sure that wasn't a limitation. And then we took that and we boiled it for the black tea, added this 8 grams in the sugar, let it steep for 15 minutes to extract all the tea goodness, which is going to be a very strong tea. Right? If you've ever brewed tea, you're not supposed to leave your tea bag in the hot water that long, right? Unless you're like most people and just put the tea bag in and walk away. But if you brew tea yourself, you're not supposed to leave it in that long. But we did. And then we cooled it off, and then we used a method called backslopping. That's what it's called. All this brewing has all these fun terms. And what that means is we took the majority of our kombucha starter was this new tea infusion, and then we added already produced kombucha, or a kombucha starter. So we backslopped some kombucha in there. For a total volume of about 300 milliliters, we put it in a 500 milliliter Erlenmeyer flask, covered it so that nothing would fall into it, and allowed it to incubate for ferment for 14 days at 20 degrees Celsius. All right. So a couple things that you should know about kombucha is that a lot of the factors that I've talked about, the type of tea, the steeping time, and the fermentation time and temperature have an impact on the final kombucha, right? So we try to minimize that, and we try to get a mid-ground. Like commercial kombuchas are typically brewed anywhere between 7 and 20 days. 14 works out good for us in the calendar, right? I can brew one day, and 2 weeks later we have kombucha. We try to minimize that. We all did all of our fermentations, like the beer, I did say that, but in triplicate. So we had 3 simultaneous things, right? So we analyzed these for pH, titratable acidity, total polyphenols, this free amino nitrogen, total antioxidant potential, ethanol, the presence of sugars, how they changed over time, and then a volatile, semi-volatile, like we've talked about. For the interest of time, we're only going to talk about, I'm going to show you the data for these, right? In part because I don't have the rest of them ready, but it's a different story. So, it's bad on my screen, but it's even worse on that screen. So this is sort of the composite, a summary of all of those brews. So on the first column, we have the ion that we converted. The next column is the concentration. The lowest concentration is always the top one. Highest is at the bottom. And then we have the T, how it was before fermentation and what it is after in the kombucha. This is the average across those. Right? Because you can't see that, because I know that, we're going to focus on these sort of 2 regions here to sort of focus what you have. In all cases, as you would expect, as we move from tea to kombucha, we see a dramatic decrease in pH. Right? So for the first one, for the bicarbonate, we see it go from a pH of 7 down to a pH of about 3.8. It's the 7 because we have the bicarbonate in there sort of buffered. But as opposed, then we looked at calcium, we went from a pH of 6.2 down to a pH of 4.17. Right? So just looking at that number, we see that there's a difference between what happened in a low concentrate with 50 milligrams per liter of bicarbonate and what happened when we have 50 milligrams per liter of calcium, right? The result, the end pH is different, right? So as you would expect, and as we sort of expect, we see that the presence of these ions do have an impact on fermentations, right? What is interesting is if we look at the next column, this total acidity, which pH is sort of a measure of the total acidity, but it's not a complete measure, right? It doesn't take into account acidic strength, for example. But what we see is if we look at total acidity, the total potential for acidity, we went from 0.035 to 0.24 with the carbonate, and we went almost the same amount in terms of with the calcium, right? We put 0.05 to 1.185. So it's a little bit less, but we still see a significant increase, which tells me that the composition leading to those 2 pHs is probably different. Right? So we are not only seeing differences in fermentation, but the resulting products are probably different. Can't say that for sure, but it's probably, right? What we do see is if we look at the total antioxidant capacity, which would be important for biological activity, we do see a decrease overall. Every time we do these fermentations, we see a decrease in this measure. But we also see differences there, right? So in this one, we went from the bicarbonate, we went from 83.8%, this measure, to 78.7. The other one, we only dropped from 89.2 to 85.4. Right? So again, there is some variability on how much antioxidant capacity is retained in these kombuchas based on water chemistry. And we see a mirroring effect of that, or slightly different. If we look at the next one, which is polyphenols, polyphenols are these larger organic molecules, right, which can have antioxidant potentials. Right? They could be involved in this antioxidant scavenging that we had reported in the previous one. But in the one where we saw a bigger increase, we actually see a decrease in antioxidant potential. We actually see an increase in the total phenols, right? Or where we didn't see much of a decrease in antioxidant potential, we actually see a fairly dramatic decrease in the total phenols. So what we're seeing here is these total measures aren't giving us the whole picture of what's going on, but we do see that there are differences here. And to sort of normalize that data, so we took, this is the change from the tea to the kombucha. Right? We can look at that same sort of thing. And if we just look at the bicarbonate, right, we see that overall we see a decrease in pH. Our total acidity sort of goes down and then sort of stabilizes. There's sort of differences in the antioxidant capacity, but that is different than when we look at this other one, the calcium, right? So if we normalize it from where the T started, that the amount of those parameters in the T, we see that there are differences as well. We haven't done the statistics on this one yet. I can't go back. On the previous one where we just look at the kombuchas, we do see statistical differences in a lot of those values. Right? So there are measurable differences there. But in general, for the kombuchas we've brewed so far, at least last year, we see a general reduction in pH from the T, which accompanied by, as you would expect, an increase in these total titratable acidity. But overall, generally a decrease in both the total antioxidant capacity and the total phenols, or polyphenols. But that's not always the case. There are some differences in there. And we see typically a statistically significant change there. Right? So now what we're doing is we've moved on and we started to investigate. This semester we were looking at, or the summer and through the semester, we've been looking at tea type. So instead of using a blended tea, which we got from like a wholesaler, we've looked at Charleston Tea Garden. You guys know about Charleston Tea Garden? People who drink tea do. Right? It is the largest and, dare say, the only commercial tea producer in the United States. There's other smaller tea gardens, but they're the largest one. Right? And they've been established, I think it was 1840s is when it was. Does that sound right? So those plants have been there for a long time, and they're probably now, I'm not a chemist, but they are probably been there long enough that there are starting to develop differences between those tea plants and teas from where they're native from. So we've been looking at how that has impacted that, and then we're going to look at sugar concentrations next. But that's the story I have to tell you today about fermented beverages. So we talked about beer, we talked about kombucha. If you're interested in any of those or want to hear about honey, feel free to ask questions now. I think we have some time for questions. Ooh, look at that. Yep.
So two questions. One is, the first one was a gluten-free one.
Mm-hmm.
Do you think that gluten has something to do with the flavor since you take it out and it doesn't taste as good?
I don't necessarily think it's the gluten. And there's evidence to suggest that the majority of the gluten doesn't survive the fermentation process. So even with barley, the amount of residual gluten is fairly low in normal beers. So I don't necessarily think it has to do with the gluten itself. I think probably the rest of the grain probably has something to do with it.
And then the second question is, in your last slide, you say it has decreased antioxidant.
Mm-hmm.
So that means maybe some of the effect they are doing is not necessarily true?
I wouldn't go that far, but I think it's probably not going to be potentially not as effective from the antioxidant perspective as just drinking tea. Right? There's a lot of evidence to suggest that the fermentation and the pH, right? We see a whole bunch of evidence for kombucha, apple cider vinegar, kimchi, sauerkraut. All of these have been linked in some form or another to increased wellness overall. I don't think it's necessarily antioxidant related. Yep.
So with the kombucha, was this just a primary fermentation, or did you do a secondary?
Yes, we did. It's just primary.
Because wouldn't you expect some changes in the profile and acidity during the secondary fermentation?
Yes. So if you don't know what it's referring, so what we did is we just took the tea and fermented it, right? Typically in a commercial, you then add additional things to it to help. Because if you had raw kombucha, it tastes like vinegar. It's very strongly acidic. There is some, if you look past the vinegar flavor, right? There is some complexity in there, but typically, as you can see for some of these other pictures, right, there's additional things in there. They'll add fruit juices, so I think that far one has like cinnamon in it, and then you allow it to sit again, so you get a secondary fermentation. We haven't looked at that yet, in part because we want to minimize the variables and not complicate it by adding these additional things.
There's a question.
Yep. Sorry.
Those compounds that you said that like created certain flavors,
Mhm.
could you use those in the kombucha or to like to keep it gluten free as well, or? Like, could you extract them in a certain way and then add them into the kombucha?
So the gluten-free, there's a couple of things that's what I'm trying to figure out how to clarify. So the kombucha itself is already gluten-free. Gluten-free only comes from things that are made with barley or wheat. So in the beer, you can add additional things to beer to enhance flavor. Right? And you can select. One thing that I didn't talk about or even address is that I gave you concentrations for those compounds and their resulting aromas, but there's what's known as a flavor threshold. So below which you will not be able to detect. The human nose or palate won't be able to detect it. So we haven't done any sort of comparison between the concentrations that we're observing and what it is in sort of that flavor threshold. And to complement matters further, we don't necessarily rarely do we distinguish one single compound. Right? Our flavor, our sense of flavor is usually a composite of multiple things. So you can, and that's typically how these brews are made, right? We brew something, we taste it. If we don't like it, we go back and change something. So there's a whole bunch of work being done in gluten-free brewing based simply on flavor. Does it taste good at the end? What ropes do we pull to make it taste good as cheaply as possible? Because the margin in brewing is actually fairly small. This is the part where I beat in a circle. Any other questions? Yep.
In your gluten-free brewing, with the sorghum versus barley, it looked like the British Dale one was similar. Is that true?
It was probably the most similar. I'm not sure I'd go out on a limb and say it was similar, but it's probably the most similar. And that's sort of what we were hoping, is that we could take a yeast that would produce one style of beer and apply it differently in this other grain to get a different. So it wouldn't necessarily make a British ale anymore. It may make an American ale, but I think it's more complicated than that. And I think I go back and forth of whether that's important, right? Because we should be able to celebrate these beers to be unique and delicious, even if they don't taste like Miller Lite, right? We can also argue with whether Miller Lite is tasty or delicious as well, but that's a different story, right? So we should be able, I think we need to be able to celebrate these for what they are, and understand that's something I've grown into. That wasn't my original goal. Right? I wanted to make something out of gluten-free grains that tasted like what I was used to, but I matured. Let's put it that way. Other questions? If I planned ahead, I would have brought kombucha for you guys to try, but I didn't. My research groups always gets nervous when I do that. They're excited the first time they try it, but the third time they're not as excited. Any other questions? All right, so like it says on here, if you have any other questions for me or if you want to be involved, if you look at that list, I have students from all over campus. There was actually some resort and tourism students in my group at one point. I have engineering students, I have biology students, I've had chemistry students, I have all kinds of different things. So if you're interested in being involved, feel free to shoot me an email and we can talk about it. that's it. Then enjoy the rest of your day.